Good morning, everybody. Hope you're all healthy and safe at home. We are going to begin a new section of our chapter, section 9.6, tangent planes and normal lines. So in this section, we are going to discuss how to find the equation of a tangent plane and the equation of a normal line. So we have studied basically in calculus, the most important thing is to find the equation of a tangent. So we know how to find the equation of a tangent line. So in this case, when we are considering 3D surfaces, we are going to find the equation of a tangent plane. So before moving to the direct formula for equation of the tangent plane, what we are going to do is we are going to discuss a few things. That is, we had introduced the concept of the gradient of a function in the previous section. So in this section, we'll begin with the geometric interpretation of the gradient function, gradient vector. So let us see that we first consider, if we consider the equation z is equal to f of xy, the level curves will be given by f of xy equal to some constant c. Just recall how we calculated or how we found what will be the level curves of the given vector. Then grade f dot r dash is 0. This is obtained by solving this or differentiating this equation and considering the parametric form of x and y. We'll go into the proof. So since grade f dot r dash, what is r dash? That is the derivative of the vector which is equal to 0. That is, grade f is normal or orthogonal to the curve at any point. And similarly, if we consider the three variable case, that is capital F of x, y, z, in this case also grade capital F will be normal to the level surface at the point which we are calculating the level curve. In case of two-dimensional, grade F will be perpendicular to the normal to the level curves given at that particular point, and in case of 3D dimensional three variable case, grade f will be normal to the level surface at the point. So let us go into the proof, or let us see how we can show that it is actually the normal or not. So let's see. For that, we are going to consider the surface which was given to us, that is z is equal to f of x comma y. Now we know the level curves can be obtained by just equating this f of xy equal to some c, right? Now let us parameterize this particular equation. Parameterize the variables, that is x and y. That is, say both x equal to, we have already used f, so we'll be using g here, that is g of t, and y is equal to, say, h of t. Okay, then what we are going to do is we will differentiate this particular equation. So in case of two variable case, we'll have the partial derivatives of f. That is, what will we get? We will get f of x, that is the derivative is dou f by dou x, and x is a function of t only, that is dx by dt, plus dou f by dou y into dy by dt, and f of xy was equal to c some constant. What is the derivative of the constant? It will be 0. Okay, that is, after we had parameterized the x and y variable, we got this particular equation. Now we know what is grade f. Grade f is nothing other than, or dou f by dou xi plus dou f by dou y j. And what is r dash of t? R dash of t is nothing other than dx by dti plus dy by dtj. So if we take the dot product of del grade f and r dash of t, what do we get? We get precisely this, right? So combining these two, we can obtain that grade f dot r dash of t is nothing other than 0. That is, we will substitute this. This side can be, this side of the equation can be considered as grade f dot r dash of t. So in a similar manner, we can do the three-dimensional case also. So let us see what is the figures are clearly given in your textbook. You can see that the figure 9 point, you can see a curve f of xy equal to c, and at any particular point the tangent vector, that is r dash of t dot, is given by red arrow. Then the grade f will be in a normal, or it will be perpendicular to this tangent vector. So this is what we just did. So we can just, I'm just reading it out. Suppose f of xy equal to c is a level curve of the differentiable function z is equal to f of xy that passes through a particular point p of x dot y dot. Okay, this level curve passes through this point. So this implies f of x dot y dot must be equal to c. Now we are parameterizing this level curve by x is equal to g of t and y is equal to h of t, such that x dot is equal to g of t dot and y dot is h of t dot. We will derive the equation, and we obtained dou f by dou x into dx by dt plus dou f by dou y into dy by dt equal to 0. Now as we introduce these vectors, grade f and r dash of t, we can see that grade f of x dot y dot dot r dash of t dot is 0. That is, grade f is orthogonal or perpendicular to the level curve at the point. That is, basically grade f is, we have given a particular function. We will first find the level surface at a particular point, and at that point we always know what will be the tangent at that particular point to the curve. So grade f is actually the orthogonal to the level curve at that point P. Now there is an example which shows the above concept. That is, we are asked to find the level curve of the surface that is given to us. F of xy is equal to minus x square plus y square passing through the point 2, 3. And we are also asked to graph the gradient at that particular point. So what do we have to find? We have to find the level curve of this particular surface. How can we do that? Now, given f of xy is equal to minus x square plus y square, we'll substitute the value of 2, 3 in this. What will be f of 2, 3 is nothing other than 5. Okay, so f of xy equal to 5 will be the particular level curve. That is, minus x square plus y square equal to 5. So that is the equation of a hyperbola. So you can see in figure 9.6.2, we have got our level curves, and now we have to find the grade f. Grade f will be actually, just have to draw a normal at the point 2, 3. Now what will be grade f? Grade f will be minus 2xi plus 2yj, and grade f at the point 2, 3 will be minus 4i plus 6j. So when we are asked to find the level curve, we just have to, at passing through any point, we just have to find what will be the value of C. Okay. So as I told in the beginning of the session, we can just move on to the level of functions of 3 variables also. That is, just like before, if f of x, y, z equal to c is the level surface of a differentiable function w is equal to f of x, y, z, which passes through any point p of x dot, y dot and z dot. Then if we are parameterizing the level curve, that is level surface, sorry. If you are parameterizing the level surface, that is x is equal to f of t, y equal to g of t, z is equal to h of t, are the parametric equations. Such that x dot is equal to f of t dot, y dot is equal to g of t dot, and z dot is equal to h of t dot. Then we will derive this equation, that is f of f x y z equal to c. We'll derive that equation and we will obtain dou f by dou x into dx by dt plus dou f by dou y into dy by dt plus dou f by dou z into dz by dt is 0. So again we'll get using the vectors of grade f and r dash, we can again see that grade f will be nothing other than it will be normal to the level surface at the particular point P. Now you can see figure 9.6.3 also. The blue shaded region is the surface f of x y z is equal to c, and we have the curve that is c, and the point P of x dot y dot, and the tangent would be r dash of t dot, and it will be the grade f will be perpendicular to this curve, or it will be perpendicular to the tangent. So next example 2 depicts the same. That is, we are asked to find the level surface of f of x y z is equal to x square plus y square plus z square, which passes through 1 comma 1 comma 1. So that is, we have to find what is the value of c. Now what will be f of 1 comma 1 comma 1? That will be nothing other than 3. So the level surface passing through 1 comma 1 comma 1 is actually the sphere x square plus y square plus z square equal to 3. Now we are asked to graph the gradient also. So what will be grade f? Grade f will be 2xi plus 2yj plus 2zk, and at the point 1 comma 1 comma 1, grade f will be 2i plus 2j plus 2k. And again figure 9.6.4, you can see clearly this sphere, and also at the point 1 comma 1 comma 1, the grade f will be a normal to that surface at that point. So that is the basic geometrical interpretation of our gradient function, which we had discussed in the previous class. So now let us move on to a new definition, that is, what is tangent planes. Now what will be, let us see what is the definition of it. Actually, let p of x dot y dot z dot be a point in the graph, and of f of x y z equal to c. Here we are considering the level surface itself. That is, let p of x dot y dot z dot be a point on the graph of f of x y z equal to c, where grade f is not 0. So keep this point in mind, that is, grade f is not 0. The tangent plane at p is actually the plane through p that is normal to grade f evaluated at P. Okay, what will be the tangent plane? The tangent plane will be the normal to the grade f. Just now we had interpreted grade f to be the grade f will be perpendicular to the surface which is given to us. So tangent plane will be normal to this grade f. So I hope the concept you can just picture it in your mind. I hope it is clear for you. That is, grade f was actually perpendicular to the level surface, and now we are stating that the tangent planes are the plane which passes through the given point, and it is normal to the grade f which is evaluated at the given point. So let us see the figure which is given in your textbook. You can see that we have a surface f of x y z is equal to c, and a point x dot y dot is z dot, and the tangent plane at x dot y dot and z dot will be normal to the grade f. The blue arrow depicts the grade f, so it will be tangent plane will be normal to this grade f. So next we have a theorem 9.6.1, which will help us to find the equation of the tangent plane. Okay, the theorem states that let p of x dot y dot z dot be a point on the graph of f of x y z equal to c, where grade f is not 0. Then an equation of the tangent plane at the point P is fx at x dot y dot z dot into x minus x dot plus fy into x dot fy of x dot y dot z dot into y minus y dot plus fz of x dot y dot z dot into z minus z dot equal to 0. So that will be the equation of the tangent plane at the point P. So given a surface and a point, we can easily find the tangent plane using this theorem. So the next example actually depicts the same thing. We are asked to find an equation of the tangent plane to the graph of x square minus 4y square plus z square equal to 16 at 2, 1, 4. That is, the surface is given to us and a point is also given to us. So first we will consider f of xyz is equal to x square minus 4y square plus z square. Now what will be f of 2, 1, 4? We need to find the tangent plane at that particular point, right? So if we are considering f of xyz is x square minus 4y square plus z square, what will be f of 2, 1, 4? It will be nothing other than 16. So that is the given surface is the level surface f of xyz which passes through the point 2, 1, 4. Okay. Now we will find fx and fy and fz and at that particular point. So what is fx? Fx will be 2x, fy will be minus 8y and fz would be 2z. Now before applying or before finding the equation, we have to note one thing, that is grade f should not be 0. So we have to calculate what is grade f. Now as we have determined fx, fy and fz, grade f is not difficult. We just have to put I, j and k. So grade f of x, y, z will be 2xi minus 8yj plus 2zk. Now what is grade f at point 2, 1, 4? It will be 2 into 2, that is 4 minus 4i minus 8j plus 8k. So this is not equal to 0. So we can apply the above theorem. What will be the theorem? The value would be fx at x dot y dot z dot, that is fx at 2, 1, 4 will be 4. So 4 into x minus 2 plus fy, it will be minus 8 into 1, that is minus 8 into y minus 1 plus 2 into 4, that is 8 plus 8 into z minus 4 equal to 0. Simplifying, we will get x minus 2y plus 2z equal to 8. So I hope it is clear. We are given the surface and the point, and first we will find the partial derivatives. We will consider the surface to be the given equation, and we will find the partial derivatives fx, fy and fz. Then we will check whether the grade f at the given point is 0 or not, because if it is not 0 only, we can apply the theorem. Then using the equation fx of x dot y dot z dot into x minus x dot plus fy of x dot y dot z dot into y minus y dot plus fz of x dot y dot z dot into z minus z dot equal to 0, it will we'll obtain the equation of the tangent plane at the given point. So let us see the next example, example 4. That is, we are asked to find an equation of the tangent plane to the graph of z is equal to 1 by 2 x square plus 1 by 2 y square plus 4 at the point 1, minus 1, 5. So what is the basic difference between this example and the previous one? In this example, we are asked to find the tangent plane to the graph of the surface which is given by z is equal to 1 by 2 x square plus 1 by 2 y square plus 4. And in the previous case, we had x, y, z, everything on one side. So we here, what we'll do is we'll consider the surface f of x, y, z to be either f of x, y minus z or z minus f of x, y. It doesn't matter. Anything we can consider. And then solve as before itself. That is, here f of x, y, z will be 1 by 2 x square plus 1 by 2 y square minus z plus 4. Okay, you can use either this surface or you can use z minus 1 by 2 x square plus 1 by 2 y z minus 1 by 2 x square minus 1 by 2 y square minus 4. Both are same. So let us see. Now what we'll do is we'll have to find f of 1, minus 1, 5. What will be the value? The value will be 0, because this is actually z minus f of x, y. That is, substituting this equation should be satisfied. So actually we will get f of x, y, z to be 0 at that particular point. So we have our surface and we have the point. Now how will we find the tangent plane? First we will find fx, fy and fz. What will be fx? Fx will be x because 2 and 2 will get cancelled. Fy will be y and fz will be minus 1. Now to apply the theorem again we have to find whether grade f at the particular point is 0 or not. So what will be grade f? Grade f will be xi plus yj minus k. So grade f at 1 comma minus 1 comma 5 will be I minus j minus k. So it is not equal to 0. So using the equation, what do we get? We get grade f at fx at 1 comma 1 minus 1 comma 5, that is 1 into x minus 1 plus minus 1 into y minus 1 and minus 1 into z minus 5 using the previous theorem. You can simplify it and you will get minus x plus y plus z is equal to 7. So that is how we can find the equation of the tangent planes. So previously we had done to find the equation of a tangent line. So now we are doing it in a 3D case. That is, we are finding the equation of the tangent plane. So I hope it is clear. Now we'll move on to the definition of normal line. So what is meant by the normal line? Let p of x dot y dot z dot be a point on the graph of f of x, y, z is equal to c where grade f is not 0. The line containing the point which is parallel to grade f is called the normal line to the surface at P. Okay, so what is a normal line? Normal line is a line which is parallel to grade f. So again, just picture it in your mind. We had a surface and we had said that grade f was actually the normal or the perpendicular at the particular point that we are given. Now, what was the tangent plane that we had discussed? Tangent plane was something which was perpendicular to the grade f, right? Because grade f was normal, so perpendicular to the surface. So tangent plane must be perpendicular to the grade f and should be lying on the surface. And what will be normal line? Normal line should be, normals are usually perpendicular to the tangent. So here normal will be parallel to grade f because grade f was before perpendicular to tangent. So I hope it is clear. And as indicated by its name, this line is normal to the tangent plane to the surface at P. So let us see how it is given in your textbook. You can see that the normal lines are nothing but lines which contain the given point which is parallel to grade f at that particular point. So next we have an example to find the normal line, and that is we are asked to find the parametric equation for the normal line to the surface which we had discussed just before. That is, in that case, what we had? We have a point here 1 comma minus 1 comma 5, and we know grade f we had calculated it to be I minus j minus k. So just now we said that the normal line is the line which is parallel to this grade f at the point x 1 comma minus 1 comma 5. So we have we just need to find the direction vector for the normal line, and we had done how to find the parametric equation given a point and a vector. We had done in the first sections, and also you can just recall it. So it will be what will it be? X will be 1 plus t, y will be minus 1 minus t, and z will be 5 minus t. I hope it's clear. We had seen the point given to us is 1 comma minus 1 comma 5, and grade f at that point we had calculated in the previous example to be I minus j minus k. So the parametric equations would be x is equal to 1 plus t, and y is equal to minus 1 minus t, and z is equal to 5 minus t. So that is the parametric equation for the normal line. Now next we are given a symmetric equation for the normal line also. So sometimes we will be asked to find the parametric equation, or sometimes we will be asked to find the symmetric equation. So the symmetric equation of the normal line to a surface f of x, y, z equal to c at a given point is given by x minus x dot by fx at x dot y dot z dot equal to y minus y dot by fy at x dot y dot z dot equal to z minus z dot by fz of x dot y dot z dot. So just remember this equation. Sometimes we'll be asked to find the symmetric equations of the normal. So if you have to see, you can just verify it, the symmetric equation for the previous example just now we had done. So I hope the concept of the tangent planes and normal lines are clear for you. So that's it for today's section. Thank you. Stay home and stay safe.